classifier. Right? So there is some map here, true, true, with these, as we sort of called them earlier, ceiling notation stuff on them. And so we defined and to be this map, true, true, from omega times omega to omega. So
Are you going to put a little square in the upper left there?
yes, okay, why not?
So 1 by itself is the universal. It's a pullback in this case. Is what you're saying?
Well, it's by the properties of set, whenever we have a sub-object, we can construct this map called the classifier such that this pullback exists, or that this thing is a pullback. And in particular, so I've given the map that does this the name and so maybe a good thing to do as an exercise, what is and of false, false? So you should have some intuition for what that should be, but do you want sort of, well, I'll give you 3 minutes to discuss with your neighbor and try and figure out how this sort of abstraction matches that intuition. Does anyone have any comments?
Shouldn't that 1 in the upper left actually be the true true crossed with 1 or something like that? You're just making that identification? Or?
Yeah, so all I need to do is write a set here. What's more interesting than the set here is the function, right? Because we're really interested not quite in the abstract way we choose to define the set, but what its image is down here. So how it realizes itself as a subset of omega times omega. Okay, so one thing I might...
If anything else goes to false, if anything else goes to true, then you don't have the universal property or something like that.
Yeah, that's essentially it. So one thing we can do is try and compute pullbacks of, well, we guess a function for this, try to compute its pullback and see what the pullback is. And I've given you a formula of the pullback right here, but this is even easier than a pullback because we have a 1 here, up here always. So let me interpret this, right? So this is the map true, and this is any map object X. So, and this is F. So what is the pullback of this diagram? So the pullback is, I mean, this abstractly could have any number of, well, okay, so this is the set true, false. And the pullback, remember, is the set of pairs of this and this that map to the same thing down here. So the pairs are just an element of X and the unique element of this, which is asterisk or star, let's say. So the question is, do both x and x and star map down to the same element, when do they do this? Or they do this when star maps to true. So we can consider this set as the set of x and x such that f of x equals true. And conversely, if we have a subset, how do we construct this map? We construct this map by sort of the opposite property. What we do is map anything in that subset to true and anything else to false. So in this case, this is a subset of omega times omega consisting of just the pair true, true. So the map classifying just the single element true, true sends true, true to true and anything else to false. So in particular, it maps false, false to false. Okay. So why do we care so much about this map, and why have we tried to construct it using so general properties? Well, this map is and in the following sense. So maybe I'll give you
which map?
This map, which I've called and. So if I give you some other predicate, so let's say we have some predicate, well, let's say we start with a subset. T is equal to natural numbers such that n is less than or equal to 10. Okay? So this is a sub-object or a subset of the natural numbers. And now we want to sort of talk about the subset, the object where t is true, which we can think of t being this predicate, n is less than 10, and evenness is true. So how do we do this? We convert both of these into the classifying maps. So we have a map from n to omega called pad of little t, right? Called the classifier of little t. And okay, let this be the classifier. And we recover the sort of the set where both these propositions are true, being less than 10 and evenness, by taking this map, so it's from the natural numbers, you get a map to omega times omega, which sort of separately describes the truth of these two statements. So it's called the pairing of t and evenness. What does it do on the number 5? Well, it maps it to a pair of true falses. The first element of that pair is, well, we ask, is 5 less than 10? And the answer is yes, so it's true. And then we ask, is 5 even? The answer is no, so it maps to true, false. And then we have a map from omega times omega to omega called and. And so what's this going to do? It's going to map this to false. We call the composite of these two maps just sort of T and E, right?
It's not really a composite, is it?
I mean, it is a composite in the sense that it's a composite of functions. So n maps to this. Sorry, this first map maps this to this, an element to this set to an element to this set, and maps an element to this set to an element to this set. So if we compose them, then we get some function from n to the sub-object classifier. And we know we can go back and forth between sub-objects, maps from some set to the sub-object classifier, and subsets of that set. So the question is, I guess, these exercises are what is the pullback of E, no, sorry, what did I say? T and E.
0, 2, 4, 6, 8, 10, each one crossed with 1 or true or whatever it may be.
Yeah. So I'm just going to call the pullback P. So the pullback is equal to 0, 2, 4, 6, 10. So the pullback, again, is the things that this thing maps to true. And what does it map to true? Well, it has, this map then has to map the natural number to the pair true, true. And when does it do that? Well, it happens when it's both in this set, so when that number is less than 10, or equal to 10, and when it's in this set, so when that number is even. So what we have is a way of talking about sort of defining the set on which both of these things are true, just using, in this case, we've used the properties of the sub-object classifier and the properties of limits. We use the terminal object, we use products, and we use pullbacks. So what this means is you can define an analog of AND in any category which has limits, or in particular finite limits, and a sub-object classifier, at least. Okay. So the question after that is sort of when this is an interesting thing to talk about. I won't talk about that in a tiny bit. So does anyone have, that's the general idea of sort of this sort of program of categorical logic, or trying to sort of recast logical operations in terms of categorical structures and then allowing us to interpret in sort of broader settings. Are there any questions about how this works or why you would want to do it?
So you would call this a categorification of logic?
Categorification, I mean, I guess some people would, because that term is not incredibly consistently used. But most people use categorification to mean replacing sort of brute facts, like there is a relationship, or A is less than B, to some sort of set of relationships. So that allows you to specify, well, A is less than B because of this proof, or by this path, or something like that. So sort of categorification replaces properties with structure. Well, this is more taking a categorical viewpoint, if that distinction really matters. Okay, so what I'm briefly going to do is tell you, I've told you how to do AND in great detail, but you might be interested, why do we need all these extra properties of set? Why do we care about them? And sort of the flip side is, how do we do, I mean, it's great if we have a logic where we can talk about A and B, but that doesn't get you very far. We want OR and for all and implies and so on, and not. So let me very quickly tell you, sort of point some connections between how you might define things like OR and these 1, 2, 3, 4 properties of set they have. So how can we define OR abstractly? Well, I want to write down omega times 1 plus 1 times omega. Okay, let's do this in 2 stages. There's a map. So OR is also going to be a map from omega times omega to omega. It's just going to have sort of a different truth table, right? It's a different subset. So we have a map here that takes, that is the identity on this factor and true, and the map true on this factor. So it's going to map true times this element maps to true, and false times this element should.
Yeah, any true.
Sorry. So I constructed this the way I want. want this to be true. That's not what I want to be doing. I don't want to be taking that map. I want to be taking this map. So I'm taking the pair, so the identity on this element and the map true on this element. So this is going to map to true, true, and this thing is going to be mapping to true, false. Right? And I have another map. I can take also this map, which is the mirror image of that. And then what I can do using the coproduct is then take this map, which combines them both. So let's see. How does this work? We'll call this F and this G. And this is sort of the co-pairing idea that we saw last time. But what is it going to do? There are 4 elements of this set, which are the 2 elements of this set and the 2 elements of this set. Those elements are going to be mapping to, say, true, 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 false, false, true, and true, true again. Right. So, okay, so the unique element times true maps to true, true. So we have some subset of, well, we have some map from here to here. To get a sub-object, we use the factorization system. And so this will take it to the image of FG. And what did we figure out the image was? Well, the image is true, 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 false, and then false, true. So we have that subset of omega times omega. Now the sub-object classifier then, so this is coproduct. Here we're using factorization. Sorry. And then now I want to use the sub-object classifier. To produce a map, if we call this M, we'll call this M from omega times omega to omega. Right. But we're also going to call this map OR. Why do we call this map OR? Because we define what this was the subset true, true, false, true, true, false. And when we push that through the sub-object classifier, it maps everything in the subset to true. So it's going to map those things to true and everything else to false. And hence be OR, in the same way that that is AND. So we can define OR this way. Next, we can define double implication quite easily through this map, which is the diagonal map. So this sends, I don't know, true to true, true, and false to false, false. And so then if we push this through the sub-object classifier, I'll call it delta for diagonal, then we get this map delta classified from this element to the sub-object classifier again, and it's going to send true, true to true and false, false to true. So that's if and only if.
Could you take a moment to write out the full square
Sure.
commutative diagram, please?
Okay.
We'll use the forest for the trees.
So what I'm trying to do is define if and only if. And this is the map. This is a map from omega times omega to omega that maps it to true if they're the same, and each element of here is the same, and false if each element is different. So what I said was that there exists a map called the diagonal map, which comes from the properties of the product, that maps true to true, true, and false to false, false. Then, using the property of the sub-object classifier, there's a map called the classifier of delta that classifies the image of this map. And how did we understand what this map should be? It sends any element, we saw that it sends any element in the image to true, and any element not in the image to false. So in particular, it sends true to true, and false false to true, and then true false to false, and false true to false. So that's exactly what we want in a if and only if. If we put two predicates and compose them in this way, then we get the set of solutions to first condition if and only if second condition. Okay, now that we've got double implication, we can define one-way implication by defining sort of, so the idea is that P implies Q is the same as, that's my mean the symbol for the same as, P and, sorry, P if and only if, P and Q. Right? So whenever P is true, Q has to be true too. And so we've seen how to define these two operators, and we can use those to define implication. Does that make sense to people? Okay. People seem approximately okay, comfortable with that idea. I'll skip past that because of the details to try and get to some more interesting things later. So the last thing I want to talk about is not, which you can define. So there is a map from using the initial object. There exists a map from the initial object to 1 to the terminal object by either the universal property of this or the universal property of this. By the property of the universal, the initiality universal property, there exists a map from the initial object to the sub-object classifier. So I'm going to call this false. And no, I'm not. That's not what I want to do. I want to say that this is a sub-object. This is a sub-object of this. This is a monomorphism. Or the empty set is a subset of a one-element set. And therefore, we can build a map from 1 to omega by the sub-object classifier. So this map is going to be the classification of this map. And so we're going to define false if we call this map U for unique. We're going to define false as the classifier of U. And what does this map do? Well, it sends the unique element of this to false. Right, because the unique element of this is not in this subset. So then we can define, now that we have implication, we define not P to be the predicate or the operation defined by P implies false. So the theme again is using these structures we see here in set, we can define our standard logical operations, and in set they have the same meaning as the standard logical operations. And we can continue, you can get for all using, as I said earlier, this internal Hom structure, and so on. Okay, but the reason for doing this is that we don't just want to do this in set, we want to do this in other settings as well, where we can talk about things not only being true or false, but true or false over some sort of time period or something like that. So, to do this we need to talk about sheaves. And sort of sheaves are a general way of constructing toposes. And sort of, if you generalize sheaves and topological spaces in the right way, you in fact can construct basically all toposes in this way. So, who is familiar with topological spaces or comfortable with the definition? Okay. I will quickly remind you of some intuition, and then that should be enough for us to run with. So, definition, so some set. So given a set X, we can talk about a set of subset of X called the set of open sets. So something open X, which consists of subsets of X, is a topology on X if, firstly, the empty set and the whole set are contained in this thing, so R open sets. Given two open sets, so when I say given two open sets, that's given A and B in this collection. That intersection is open, and then given any number of open sets we like, I guess this is a subset of X, then the union of all of these things is open. Okay, so the open terminology comes from, say, open enclosed intervals on the real line, or open intervals on the real line. But that being the definition, the idea is we have some space, and we want to sort of describe what it means to sort of be a connected set of things. And if there's some notion of distance, then what we want to sort of have is that if an element is in the open set, then everything near it is in that open set. So if this is A and we have some point in here, then sort of everything near it is going to be in there. So there's really a sort of fuzzy boundary to A, just like there's a sort of fuzzy boundary to the open interval, let's say 0, 5, where if we can find something in the set, say epsilon, then there's still something like half epsilon also in the set. That's we can still always find something smaller and above 0. But somehow this is the right notion of what it means to talk about sort of space and coherence things. Then these axioms are saying that if we take two open sets, then sort of this thing can be considered open, and this thing, the union, can be considered open, and so on. It has sort of, every point has sort of its neighborhood around it in it. Okay, so what a sheaf does on a topological space is assign each open set some set of readings that can exist on this set. So you might think of a sheaf, say, the Earth as a sphere, which is a topological space, which has sort of these notions of nearness. So if we draw kind of a circle, if we sort of pick out regions, they form open sets. And to every region, we can associate something like a vector field, which might be the wind speed at every single point. And so the set of all these vector fields forms a sheaf that says, sort of, given the space, what sorts of things can happen on this space. And in fact, this sort of provides an alternate definition of understanding of space. So instead of focusing on what the points are of the space and what the regions are, or the subsets are, you start focusing on more of what can happen in that space, and that's sort of how the notion of sheaf comes about. So, what is a sheaf? So, definition then, a pre-sheaf, or topological pre-sheaf at least, is a functor from open X up to set. So we'll call this functor F. What does this mean? So OpenX is a poset ordered by inclusion. It's a subset of the power set, and we know that every subset of a power set is a poset, and every subset of a poset inherits a poset structure. Up means we flip around the ordering, and this means to every open set we associate some set, again the set of readings or whatever, and to every inclusion we associate a function in the other direction called a restriction map. So what we have then is to A and B, we have...
Does the superscript up here thus mean that you're looking at the opposite poset?
Yes.
So
now that's why inclusions tend to restriction functions.
Okay.
So we have sort of this Hasse diagram here, which says that A intersection B sits inside A and B, and what we get is some set f of A, set f of B, and a set f of A union intersection B, and then we get functions, so this is the up, going down, that says if we know everything that can happen on B here, we can talk about the things that can happen just on where B intersects with A. Okay, so Sheaves has this notion of restriction of behavior. If we know global behavior, we can infer local behavior just by restricting our view. Sheaves go the other way as well. Sheaves mean there's a sort of a tight correspondence between local and global. So let's write down the definition. Let's see. So given all this stuff, if we have some collection of open sets of some topological space, and we write U for the union of these things, then, okay. Call S in each of these things. So call some collection of elements of each of these sets. So we pick an element of here, an element of here, and an element of here. A matching family if, okay, so I'm just going to call this restriction of A to A intersect B.